Hello everyone, I am Dr. Ritish Kumar. I am going to give the lecture on the subject of microwave and radar engineering, and the topic is radar. So before starting the topic, first we need to understand what is the radar. So the full form of radar is radio detection and ranging. So all the things specified within the name, radio detection and ranging. So uh, what it specify all the things is detected by the radio waves, right? So uh, radio waves helps to detect the target, the properties uh, such as the material of the target, how much far it away from the radar, whether it is moving towards the radar or whether it is moving away from the detector points. So all the things we will learn about in this topic. So first we will discuss about the frequency band, then we'll move towards the radio radar range equations, and then we'll discuss about the Doppler radar. So let's begin with the some frequency bands, which is the standard frequency band. The name of the frequency bands, such uh, as I can say, um, this is millimeter wave band, right? This is K band. The all of the bands such as K, KU, K, X, C, S, L, ultra high frequency, very high frequency, and high frequency. And you can clearly observe here the corresponding frequency range is specified within the table. So millimeter wave band starts from 40 gigahertz to 300 gigahertz, and the corresponding wavelength we can say 7.5 millimeter to 1 mm. If you talk about some standard microwave frequency bands such as L, S, C, X, KU, K, K. So L starts from 1 to 2 gigahertz, and the wavelength starts from 3 centimeter to 15 centimeter, and S is start from 2 to 4 gigahertz, and corresponding wavelength equal to 15 uh, uh, 1.5 centimeter to 7.5 centimeter, and relative C band starts from 4 to 8 gigahertz, X 8 to 12 gigahertz, and KU 12 to 18, and K 18 to 27, and K 27 to 40 gigahertz. So you can clearly observe here these all bands are mainly is used in the satellite communication and microwave experiment. So in the lab you can have the setup microwave test band setup within the range of 8 to 12 gigahertz, right? So this band is nothing but an X band, we can see. So in our laboratory we have X band components, right? Such as X band waveguide, X band attenuator, X band mean terminators, mass terminator, etc. So all the dimensions of the waveguide is chosen in such a way so that it can work in the X band application, right? So rest of the bands such as ultra high frequency band, very high frequency band, and high frequency band have the frequency range from 0.3 to 1, and 0.03 to zero point 0.3 gigahertz, and 0.003 to 0.03 gigahertz respectively. And corresponding the applications of these bands such as television field, satellite field, and etc. we can say. So you need to remember all these kind of standard microwave bands for various applications. So I think this frequency band is clear to all of you. Now coming to the uh, point, radar block. This is the basic block diagram of radar. So how can we can able to find the target the location of the target, and the other properties as how much it is how much the site it has, and the environmental property we can also justify with the help of target. So you can clearly see here, this one is the target. Target can be anything, right? Here we have taken the example of aeroplane, and now the this one is the antenna, right? Yeah. And here we are using the duplexer tools. Here then we have the receiver, right? Signal processing, then data processor. We have, at last we have a display device through which we can identify the location of the target, right? Here we are using the duplexer tube, duplexer switch. Here you can clearly observe here a single antenna can be work as a transmitter and receiver. With the help of duplexer switch, we can make this antenna as a transmitter and receiver. So what kind of antenna we are using here? As you can clearly see here, this is a kind of reflector antenna, as we have read in the antenna subject. So this is a reflector antenna, and this antenna has a property of directional radiation. So if we want to know the exact location, or in the accuracy of the location, so we need to have a more directional antenna. Why? Because how we can achieve the more directional antenna? So if you correlate the thing with the directional radiation pattern, so in the directional radiation pattern always has the low half power beam width, right? And it has the this is a kind of directional radiation pattern. So if we have to have the more directional radiation pattern, this beam width should be as low as possible. And to know the exact location of the target, this beam width this beam width should be as low as possible accordingly, right? Now you can see here the process of here we are doing the analysis over the signal that we have received through the receiver, right? The thing is, how we can say this antenna can be act as a transmitter and receiver by the principal law of reciprocity theorem. And here we are doing some signal processing over the signal that we have received through the receiver. So this signal we can modify the signal by using some signal processor, so that we can able to encrypt the data, and so that no one can identify no one other person can identify the exact location of the target, so if you want to encrypt the data. So whatever the signal processor you want to do, you can do the process using the signal processor and data processor. At last we are able to find or see the data over some display device. So as you can see, you can able to find the location, size, and environmental condition, right, etc. With the help of radar. That's why we call this radar is a radio detection and ranging. So with the help of radio waves, we are able to detect and the location of the target of we are able to detect and the location of the target with the help of radio waves. This is the explanation of the radar full form, right? Now the next we will discuss about the radar range equation. So with the help of this equation we are able to do the mathematical analysis of the range of the or location of the target. So as we have mentioned here, the radar range equation relates the range of radar to the characteristics of the transmitter, receiver, antenna, target and environment. As we said in the last slide, it is used as a tool to help in specifying radar subsystem. So here we need to know the power density, that is watt per meter square at a distance of r. If the antenna is omnidirectional antenna, then the power density will always be equal to Pt upon 4 pi r square, where r is the radius of sphere, right? So Pt is the transmitting power, right? So here we are using the omnidirectional antenna. Suppose in the case of, if we in the radar system, always be the antenna should be directional. So if the antenna has the gain equal to z, then this power density, how much the power will be transmitted through the antenna in a particular direction which has the gain of g, then this power density is multiplied by the gain of the antenna. So this power density will be equal to Pt gt upon 4 pi r square. Now if the radio waves generates from the antenna strikes over the some target, and the target has some area that is equal to sigma square, right? And this area is also known as radar cross section area, right? That is also known as RCS, radar cross section area. So how much power is reflected from the target? How much power means the how much percentage is reflected from the target, and this is the power, which is the percentage of the transmitted power, is sigma upon 4 pi r square. So this percentage is multiplied with the this power density, right? Ptg upon 4 pi r square and multiply by sigma upon 4 pi r square, right? So this is a power density, that is watt per meter square. Now now the power delivered to the receiver, suppose the reflected power, I am talking about, if you look into the block diagram, the reflected power again strikes over the antenna, and in antenna has some area. That area is known as aperture area. So only this kind of radio wave is received through the antenna. And suppose if the aperture area of the antenna is equal to a, so how much power we will be receiving at the receiver side? So this power density is multiplied by the area of the effective area of the antenna, that is A. So received power is nothing but equal to Pt gt upon 4 pi r square into sigma upon 4 pi r square into A. This comes into the unit of watts. So this is received power at the receiver. Now the thing is, how much range we can able to detect, or that is the maximum range of the radar, or we can, in terms of we can also say like the minimum detectable power that we can receive through the receiver. That range is known as maximum radar range. So from the previous formula, we can we can directly find the equation of R maximum through this equation. So this equation is looking like in this way, right? R max is equal to PT GT AE upon sigma upon 4 pi A square. S minimum, this is S minimum is the minimum detectable power, right? So this is an important equation that you need to remember it. So this is a maximum radar range equation. Suppose as we already read the formula of gain of the antenna, that is equal to G upon 4 pi upon lambda square into A. As you can clearly observe here, gain is directly proportional to the effective area of the antenna. If the effective area of antenna is large, then you will get the higher gain. So if you put this equation, this formula of G, gain of the antenna, is put you can keep this formula into this equation. So after putting the formula in this equation, you will get the R maximum equation in this form, right? So we can say the R maximum is directly proportional to the square root of A. So if you use the larger size of antenna, then you will have the more radar range, right? So this is the basic equation. Also we can say this is a Friis equation that already learned in the satellite communication system. This is nothing but a radar system as well. Now the next is the Doppler radar. So what is the Doppler? So if we move towards the basic concept of the relative velocity that we already read in the physics, that is if we move in the same direction, then you will have the relative velocity less compared to if you move in the opposite direction. So same concept you can have in the Doppler radar. Suppose if the target is moving towards the receiving antenna, then the frequency will increase in that case. If the target is moving away from the receiving antenna, then the received frequency will decrease. That is the main basic phenomena that you can have in the radar, and this concept is known as Doppler, and this effect is known as Doppler effect. Also in terms of frequency, we can also say like Doppler frequency shift in the radar. So all the things the terms is echo is nothing but a reflected signal that is received from the target after the radio waves strike over the target, right? So that is as you can see in the last point, the presence of the frequency shift in the received echo signals in the radar due to the moving target is known as Doppler effect. The frequency shift is also known as Doppler frequency shift, right? So the main thing, the radar radiate, as I already discussed, the radars radiates electromagnetic waves on the also known as radio waves towards the target for the detection, also to obtain details of the target. So I think this one is clear to all of you, how the frequency increase and frequency decrease by moving the target. So by taking the reference location of target, you can able to find either the target is moving towards the receiving antenna or away from the receiving antenna. That is all about the Doppler about. Now we find the Doppler frequency which is related to the relative velocity of the radar. So you can clearly see here, this is the Doppler angular frequency, which is represented by omega d is equal to 2 pi fd, and this is a angular frequency. So so this is also we can say d phi over dt, and phi is the phase. Phi is the phase. So phi is equal to phase is equal to 2 pi y upon lambda, and traveling path difference. So path difference, if you see the total path traveled by the radio wave, that is transmitted and reflected. So total distance is transmitted and reflected, and this distance is equal to r. So total travel distance is equal to 2r. So this is nothing but 4 pi upon lambda into r, right? I think this is clear how it comes. So omega d is equal to 4 pi upon lambda dr by dt, and dr by dt is nothing but the velocity of the target, 4 pi upon lambda into Vr. So this equation you can write also 2 pi to 2 pi cancelled out here, and you will get FD is equal to twice Vr upon lambda. So FD is directly proportional to relative velocity of the target. So as you can see in the physics, the relative velocity. So if relative velocity increase, so frequency will increase. If relative velocity decrease, frequency will decrease. That is the concept of Doppler radar. So suppose if the radar, if the target is having some angle location, right? So this one is receiver, and this one is receiver, right? And this one is target. Suppose this one velocity is representing a Vr. So this velocity will becomes Vr cos theta, right? So this equation is replaced by twice V cos theta upon lambda, right? If the target is about at some angle theta. So there would be some two cases you will have. At theta is equal to 0, the Doppler frequency will have the maximum value, right? If the Doppler frequency is 0, at 90 theta is equal to 90 degrees, we will get the Doppler frequency is 0 when the trajectory is perpendicular to the radar of line of sight. And I think this Doppler frequency, Doppler radar or Doppler frequency shift, and the some microwave bands is clear to all of you. So at last I will conclude the topic with radar. Radar is nothing but the detection and to find detect and to find the location of the target with the help of radio waves. We are using some technique that is known as radar. I think this the radar topic is clear to all of you. Thank you.